and I welcome you all to this session of ICMW CAIPEEX convective case discussion. So the first speaker is Dr. Sachin Patate. So he will give an introduction to the case and overview, and then he will present his case results. So I invite Dr. Sachin Patate to deliver his lecture.
Okay, so shall we begin? Okay. Okay, can you see my screen now?
Yes. Yeah.
Okay. So good evening, good morning, and good afternoon, everyone. My name is Dr. Sachin, and I'll be giving the overview of the CAIPEX case study, monsoon deep convection. Actually, most of the work was done by Gayatri Urankar, but she has other responsibilities. So I'll be presenting this work on her behalf, you can say, and I may have to redirect some specific questions to her if she's around. Okay. So we all are aware about the objective of this case study. The main objective of this case study is to investigate the small and large domain impacts on aerosol effects with alias and cloud resolving model, and investigate the impact on mixed phase cloud process in the polluted conditions. So we have four specific focus points. First one is to investigate the aerosol effect on mixed phase cloud process and impact on precipitation. Next objective is initialization from different domains on cloud aerosol interaction. Third one is impact on domain size on cloud aerosol interaction. And last one is impact of environmental parameters on deep convective clouds. So the case that we selected for the model comparison is deep convective clouds that observe on 27th October 2011 uh, in the leeward side of the Western Ghat on Mehbubnagar. This is the rain shadow region and it receives almost 20% less rainfall than the windward side of the Western Ghats. And in the satellite imagery, we can see deep convection with both shallow and deep convective clouds resembling a mesoscale convective cluster near this coastal region. This system moves west and northwestward inland during the Diurnal cycle. So these convective clouds over this study region, I'll say, which is around 200 and 150 kilometer. This cloud was profiled by CAIPEX aircraft uh, and also monitored by the C-band radar. So the corresponding flight track by CAIPEX aircraft is shown here. This aircraft profiled this cloud till around 8 kilometer, and so the CAIPEX aircraft was uh, it has a very latest instrumentation on board. So the if cloud effective drop cloud effective radius and its vertical variation is shown over here. We can see that it varies from 2 micrometer to 12 micrometer near cloud top, and this color bar indicates the cloud liquid water content, and we can see the maximum cloud liquid water content is 3 gram per meter cube. So the SQT plot at 1330 LST over the study region is shown over here. We can see that surface is really moist and the surface mixing ratio was around 18 gram per kg. The surface dew point temperature was 23 degrees Celsius, which indicate the warm base cloud system. LCL is located around 853 HPA. The temperature at LCL was 18 degrees Celsius. The convective available potential energy for the start of the convection is around 1900 joule per kg, and the total column precipitated water was around 5 centimeter. So the aircraft also indicated that the subcloud aerosol is reaching as high as 3000 per centimeter cube, which indicates that these clouds were growing in a really polluted environment. So we have a CCN counter on board, and we can see the CCN spectra from that CCN counter here. And we can see that the CCN number concentration around 1000 per centimeter cube at 1% supersaturation. So basically, the CCN type was continental, and in the next few next slides, we can see that for the control run, we consider the initial CCN number concentration around 1000 per centimeter cube at 1% supersaturation. So what I've shown here is the combined drop size and particle size distribution from various instruments that were on board on the CAIPEEX aircraft. Uh, and the averaging was done for the specific time that we can see here, and the altitude and corresponding temperature is shown here, and we can see liquid water content. So the important point is to note here is that uh, the top size distribution and particle size distribution from various instruments shows very good agreement among them, which shows that the measurements conducted in these clouds were highly reliable. We can see really good agreement over the overlapping regions, so it gives us the confidence about the aircraft measurements in these clouds. So to get an idea about the ice particle habits in these clouds, what I shown is the compiled images of ice particles from 2D probes, and the temperature and corresponding altitude is mentioned on the left side. So we can see a lot of variety of ice particles like needles and columns, plates, chain aggregates, graupels, and we can also see supercool drops at the warmer temperature. We can see the width of this strip is around 1.28 millimeter. So we can see graupel particles as large as 1 millimeter at 6.2 kilometer. And we can see presence of needles and columns around 6.2 kilometer. And temperature at this altitude is around minus 5.6. So this is the region where the second ice formation through Hellermoser process can happen. And we can see there is a lot of graupel which can act as rhymus, and these rhymus can then grow by vapor diffusion to needles. So this indicates that the second ice formation through Hellermoser process was highly active in this cloud. And most of the particles were highly rhymed, so it also shows that the rhyming was efficient ice particle growth process in this cloud. So we simulate this deep convective case using weather research and forecasting model, and the specification of this numerical simulation is shown here. So we use three nested domains uh, with horizontal resolution of 27 kilometer, 9 kilometer, and 3 kilometer. This third domain was set over the study region, which I showed in the first slide. So various physical parameter schemes that we use for the simulation are shown here. Initial and boundary conditions uh, were given using 6-hourly and say final analysis, global analysis data. We use fast version of spectral wind microphysics for model simulations. The simulations were done for 24 hours. To investigate the aerosol effect on cloud microphysical properties, we did some sensitive studies by varying the initial CCN number concentration, like low CCN, where we have initial CCN number concentration is 100 centimeter cube. Then we have control run with 1000 per centimeter cube CCN number concentration at 1% supersaturation. And then we have a very high CCN case where the initial CCN number concentration was 3000 per centimeter cube. So here what I've shown here is the comparison of simulated cloud properties with available aircraft observations. The simulated temperature is compared with CAIPEEX aircraft observations, and it shows good agreement. The simulated relative humidity is slightly higher than the CAIPEEX observations, but the overall vertical structure is well captured by the model. And the effective radius is in good agreement with the CAIPEEX observations, even liquid water content. So we have a slight underestimation of ice water content near cloud top in the model simulation. And then it is important to compare the, since we are using bin model, it is important to compare the drop size distribution and particle size distribution from model simulation with observations, because the microphysical structure and precipitation depends on the shape of this spectra at all stage of cloud evolution. So what I shown here is the drop size distribution from model at in abrupt with W greater than 2 meter per second, and we also compared the particle size distribution from various instruments on board with model simulations. So overall, we can see that there is a good agreement of DSD and PSD from model simulations with observations. So it gives us the confidence that model has really simulated the particle size distribution and drop size distribution, which is comparable with the aircraft observations. So here what I've shown is the time evolution of liquid water path, ice water path over the study region, and we also have shown the accumulated rain and rain rate for the study region. We can see there is a, overall there is an increase in liquid water path and ice water path with increase in CCN number concentration. And about accumulated rainfall, we can see that there is a around 20% increase in rainfall when we have higher CCN number concentration. But this is for the averaging. When we do averaging over the study region, if we average the uh, rainfall over the whole domain, we don't see much difference in the accumulated rainfall. Okay, so here we show the important cloud parameters and their vertical variation for various runs. Uh, First panel is maximum cloud droplet number concentration. We can see it reaches 1000 per centimeter cube in the highest CCN uh, uh, number concentration simulation. And for clean case, we can see it's around 100 per centimeter cube. The cloud droplet effective radius reaches 12 micrometer, around 4 kilometer in the clean case, and it means that the warm rain process were really active in this clean case. But in control run and highly polluted run, it never reached 12 micrometer, which means the warm rain process were suppressed in high CCN cases. And we can see that there is a increase in cloud liquid water content when there is increase in CC number concentration, and it can be attributed to the second indirect effect where we have the separation of warm rain process which retains the cloud liquid water content in the cloud for a long time. However, we can see even though the warm rain process are suppressed, we can see there is an increase in rainwater content. So it is likely associated with the enhanced melting of the ice hydrometeor. So here we can see the vertical structure of various ice macrophysical parameters like ice content, snow content, and graupel content. We can see with increasing CC number concentration, the mass of all hydrometeors is increased. We can see a bimodal structure in ice number concentration. So the increase in ice number around this 12 kilometer is due to homogeneous freezing of cloud droplets. And the second mode here around 6 kilometer is due to halotmos process. For to investigate this, if this peak is really due to halotmos process, we did additional simulations with and without halotmos process, and we can see when the halotmos process is on, we can see that this peak is present at 6 kilometer, and when it is off, we don't see any peak here. So this peak in ice crystal number concentration around 6 kilometer is due to the secondary ice production due to halotmos process. So it is also interesting to note the CCN effect on drop size distribution and particle size distribution. We can see that under polluted conditions, this drop size distribution shifted to smaller diameter because there is competition for available moisture due to increase in CC number concentration. However, we can notice the that raindrop size distribution becomes broader with increase in CCN number concentration. And if you look at the graupel size distribution, we can see that under polluted conditions, the graupel size distribution becomes broader, and we can find the graupel particles at much higher altitude in polluted condition due to increase in uh, updraft. Okay, so this is about the overview of this CAIPEEX case study, deep convection, monsoon deep convection, and this is well described in Gayatri et al., which is which is we can find this in JAS in 2018. So, so then we also simulate this case using a large AD simulation model. And the purpose of this extension of this study is this diagram, where we can see that the average cloud droplet number concentration for each case from first phase of CAIPEEX versus boundary layer water vapor mixing ratio. And the marker size indicates the effective radius for each case. and the marked colors indicates the subcloud aerosol number concentration. So we can see that there is a lot of variation in boundary water vapor mixing ratio. It varies from 5 gram per kg to almost 22 gram per kg, and we can see a lot of variation in subcloud aerosol number concentration. So the question arises: what will the effect of this combined effect of this change in boundary water vapor mixing ratio and subcloud aerosol number concentration, or CCN number concentration, we can say. So we suggested the experimental setup for our alias simulations. It is given here. It's already there in agenda, so I'm not going to describe this in details. So the objective of this case study is the fourth one: impact of environmental parameters on deep convective clouds. Okay, so the model setup is given here. So we use WRF large eddy simulation model for the simulating this case. We use 20 by 20 kilometer domain with horizontal resolution of 200 meter, and a model top was located at 15 kilometer. Vertical around 60 meter, 30 meter, I guess, and time step was 1 second. Duration of simulation was 6 hours, and output was taken at every 2 minutes. So we use fast version of spectral in microphysics, similar to what we use for the earlier study. And various sensitivity experiments were conducted by varying the initial profile of mixing ratio and initial CC number concentration, we can see here. So we varied CC number concentration from 100 per cc to 3000 per cc, and we also varied the mixing ratio profile by 10%, 20%, and we also decreased by 10%, 20%, like that. And we also conducted a few simulation by switching off and on the Hallet Mossop process. So this is the model validation. Overall, I can say that I will see that the model simulated cloud parameters are in good agreement with the observations. So this is the time at evolution of simulated cloud parameters for clean conditions. We can see cloud water, ice, snow, and graupel. We can see on the left side we have drier conditions, and on the right side we have moist cases. We can see that with the increase in moisture, there is increase in cloud water, and with increase in moisture, we can see there is early onset of ice phase in these clouds. Also, the ice mass increases with the increase in moisture. So this is for the polluted cases, and we can see there is an increase in supercooled liquid at near cloud top under polluted conditions, and also there is an increase in ice mass, snow mass, and graupel under polluted conditions. So it is important to know the cloud phase to understand the complex process of precipitation formation. There are many formulas available in the literature to determine the mixed phase of cloud. So we use this formula, which is mentioned here. So I plotted the time evolution of this phase fraction for clean and polluted conditions, and we can see the time evolution for various moisture sensitivity experiments here. This is for clean condition, and we can see various sensitivity experiments with the change in moisture. This is for polluted condition, the right side panel. So we can see there is a enhancement in mixes under moist and polluted conditions, and we can see early appearance of mixed phase with increased moisture in both clean and polluted conditions. So talking about the accumulator precipitation, there is increase in precipitation after the onset of mixed phase, and overall there is increase in accumulator precipitation with moisture as well as with increase in CCN number concentration. And the CCN effect on precipitation is more pronounced in moist cases. Okay, so here what I've seen is the P mean values uh, of various cloud parameters to get an idea about how this combined effect of moisture and aerosol uh, is going to affect the microphysical process. So we can see there is increase in cloud ice with moisture as well as aerosol number concentration. There is increased snow and graupel mass. We can also see the increase in condensate loading and precipitation. So overall moisture effect which means we change the mixing ratio by 20%, is greater than the aerosol effect, where we change the CCN number by 10 times. However, there are a few processes like rhyming rate. We can see that the change in CCN is really has a big impact on rhyming rate. So, so there are a few processes like rhyming and then the conversion of cloud liquid to rain. The These processes are very sensitive to change in CCN number concentration. So here, what I've shown is the size distribution of ice particles in the Hallet Mossop region for various moisture sensitive experiments in clean and polluted runs. So we switch on the Hallet Mossop process in one run and then we switch off. So this solid lines indicates the Hallet Mossop process is on and the dotted line indicates the Hallet Mossop process off. So overall, we can see there is a considerable amount of ice mass was generated by, or ice number was generated by this Hallet Mossop process, not ice mass. This is ice number concentration, and the contribution of this process to total ice crystal number concentration increases with moisture and pollution. Uh, it's not shown here, but we showed that there is not much effect on accumulated rainfall from this Hallet Mossop process because its contribution to ice mass is not that significant. So, in summary, the boundary layer moisture has a big impact on cloud development. So, the clouds developing under moist environment have lower cloud base, and we have deeper clouds. These clouds were characterized by more supercooled water. We have earlier onset of mixed phase in this cloud. We have high mixed phase fraction and enhanced precipitation. The highest CCN environment affect the cloud droplet size, and also there are some process like rhyming rate, and there's also increase snow mass when we increase the CCN. So overall, the aerosol effect on cloud phase and precipitation are more significant in the moisture environment, and considerable amount of ice number concentration comes from the atmosphere process, but its impact on precipitation is really small. And that's from the earlier simulations. Thank you. If you have some specific questions, you can ask. I think
Okay, so now we have time for a few quick questions.
yeah, I think I was too fast.
Yeah, you are so fast. Yeah.
Can I stop sharing or
Yeah, yeah, you can stop sharing your screen.
okay, fine. Okay. Yeah. So I hope Gayatri is around if you have some technical questions.
Yeah, she's there. Yeah.
Okay.
Yeah, I think we start. Okay, Chunzong has a question. Hold on. All right, Chunzong, you are spotlighted.
Okay, thank you. Okay, Sachin, I have a question.
Yes.
So, how did you set the relative humidity sensitivity tests? Did you increase the relative humidity for the whole domain or some other settings?
Yeah. I mean, we changed the initial profile of uh, uh, mixing ratio.
So, you need to work, right?
Maybe maybe Gayatri can explore more if she's here.
Hello, hi.
Okay.
Yeah, this is for LES simulation.
Yeah, Sachin, can you
Yeah.
just quickly say, do you change the moisture through the entire column or only part of the atmosphere?
We
Yes.
change our entire column.
Okay.
Yeah, Gayatri, you are now spotlighted.
Okay.
You can answer to audience.
Yes, Gayatri.
Uh, yes, yeah, I think Sachin answered it. We changed for entire column, and this is the LES simulation. So the initial sounding was altered with change in initial mixing ratio profile.
Okay, thank you. I have another question. Can you go back to the summary slide?
Okay. Yeah. Yeah.
Share your screen, Sachin.
Oh, yeah, okay. I forgot to share. Okay. Okay. Can you see now?
Yes, yes.
Okay.
I can't find it.
Oh, still.
When you are
Mm,
sharing, Chunzong, you need to click on Sachin's screen.
I think now Gayatri is on podium, maybe because of that. I shared my screen.
Yeah, I can
So
see.
for some reason, I clicked the screen from Sachin, but I can't see the.
Can you see the
Yeah,
screen?
I see it.
Oh, okay.
Yeah.
Yeah.
Um, so the conclusion for the moist environment, the mixed phase fraction is high.
Yes.
Can you, can you explain it? Is there any physical mechanism high mixed phase?
Uh, you mean why mixed fraction is higher in moist environment?
Yeah.
Uh, yeah, because in moist environment we have more ice, more graupel,
Mhm.
because all these processes are linked. So we have high moist means there's high supersaturation, ice supersaturation. So the deposition growth is really high, and then we also have considerable amount of graupel coming from the end of freezing in these moist cases. It makes the ice onset quite early, and hence the increase in mixed phase fraction.
Okay.
So
Thank you.
overall there is an increase in ice mass as shown in the time height evolution of these hydrometeors.
Okay. Thank you.
So, any other questions? Yeah,
We
there
have a
is
hand
one more
raised.
question. Yeah.
Okay, I just missed to see whether you have given this boundary conditions time varying, or it's like a fixed boundary surface boundary condition.
It's fixed boundary conditions. This is totally idealized simulation. So we
Yeah,
just wanted.
idealized. I mean, prescribed surface fluxes or surface temperature or time varying,
It
because
is
it's
prescribed, and it is surface flux were estimated based on the surface temperature and surface mixing ratios. We don't have
yeah only
specific
for a fixed time or time
fixed,
varying.
fixed time.
Fixed time. Yeah, that's what.
Yeah.
And also radiation. Also, it's like a prescribed
You,
or
oh,
in the
you mean for the LA simulations?
yeah Elias solution.
Yeah, it is fixed.
Okay. Okay.
Okay. So, any other question? We have 1-2 minutes more. So, if any other question, then we can discuss.
Can I say something, Sudarshan?
Yes, madam.
Yeah, actually, Anuros was asking about the surface boundary condition. Actually, our objective was to just recreate the cloud that is in the growing stage. In most of the simulations, we focus on that because CAIPEEX observations are basically focusing on the growing stage of the cloud until the precipitation. So most of our objectives were centered around that period. So it is a just we use a surface temperature. Indeed, in WRF basically we are initializing with the surface temperature, and the fluxes are computed, and fluxes do vary during the integration.
Yeah.
Just
Thanks, ma'am.
wanted to yeah.
Yeah, thanks, ma'am. Yeah, I just thought that since it's a land, I agree with you that during the growing phase, it may not impact much. Still, I just thought that whether in land, whether you have added or not. That's why I just thought that to
Yeah.
ask.
Yeah,
Okay.
there is no land, but we use a observation from observation.
Yeah. Means roughness length in terms of, yeah.
Okay, so we'll move to next lecture that will be delivered by Professor Wojtek Grabowski. So I invite him to deliver his lecture now.
Sachin, you need to move to other place
Yeah,
to
yeah,
discuss.
Sachin, you move from that
Okay.
place.
Oh, okay. Okay, I need to move. Okay, fine. Is that okay?
Yes.
Okay, thanks.
All right. So I need to start sharing my screen.
Oh, sorry.
So now the question is, do you see my screen?
Yes, we can.
Okay.
Yes.
Okay, very good. So Tara asked me to present some background on the CAIPEEX case, and I'm really happy to do it because I've been seeing basically the growth of the Indian cloud physics community around this case, around those simulations. So this is really kind of a review, if you like. You will see that there will be some surprising pictures for some of you, maybe, at least 3 people in the audience. Now, I want to start with this picture that Tara showed initially. And, if we are sitting in the room, I would see whether people got the point or laugh at it or not. Of course, I cannot do it. I mean, I can't hear the audience. That was when I visited India a few years back, and we've been planning with Tara to have the conference dinner at a place which have this kind of cutoff. You can see that I'm standing behind of cutoff, so this Maharaja is really a joke. But I wanted to show it again because I didn't really know whether people got the point or not. This is clearly a cutout, and I'm standing behind, and Tara took a picture and is showing it. So, of course, I still don't know whether you're laughing at it or are embarrassed by me showing it. But anyway, I still decided to kind of show it again. So anyway, so what is CAIPEEX? CAIPEEX is a major effort of the Indian government to understand precipitation processes. I mean, this is my interpretation. I mean, I don't think this is written like that in any document, but that's my kind of thinking about it. That's a major effort of the Indian government to understand precipitation processes and to assess whether and how increasing rainfall through cloud seeding is possible over the Indian subcontinent. So to me, there are 3 aspects that are worth kind of discussing and putting into context of cloud physics community and cloud modeling workshop in particular. So there is science that CAIPEEX really addressing specifically for the Indian subcontinent, but I think way beyond just Indian subcontinent. There is more, and I will show it to you. There is a development of research infrastructure, Indian research infrastructure, and I will not talk about that, but I'm pretty sure for many of you this is obvious. They now have an aircraft which they didn't have initially. They had to hire an aircraft to do it. The radars, the observation sites. I visited a site under construction that was maybe 7-8 years ago. So this is now operational. So that's great. That's really shows the commitment of the Indian government to show this important problem, because of course, which is fairly obvious, but perhaps needs to be said again, that the rainfall is critical for the Indian, industries, for the Indian government, and for the Indian people. Weak monsoon means not enough crops. Too strong monsoon means flooding, as happened a couple of years ago in Tara's original place in Kerala, I think. So it is an important point, but also, which I will show at the end, it's also education of new generation of Indian scientists. I think this is important if this research that started with IITM people, Professor Goswami, Tara, and others, it's important to continue. So let me give you a short overview. So this is a paper published in Indian kind of all science journal, Current Science, which kind of documents, discusses the experiment and previous and the preliminary results. So that's about a decade ago. So some of those slides that I will show, Sachin already showed. So what this right picture shows is basically the flights of around cities that were involved in CAIPEEX, I think, initially. So Pune is somewhere here. And then this picture Sachin already showed. So basically this project involves pre-monsoon clouds when the atmosphere is very dry, it's quite polluted, and it's basically almost no clouds in the morning, if you like, typically, but then convection develops during the day, down to kind of transition in monsoon when there is more moisture, less pollution, if you like, so on and so forth. But not necessarily. Here you get a very polluted environment, but still clouds develop very large effective radius. So anyway, really complex interaction between clouds in different regions. I'm assuming some of those are in different regions, and maybe some of those numbers explain where they were, where this data comes from. But you can kind of appreciate the variability of those clouds and conditions in which they develop. So talking about specific science, that's one of the aspects that many of us were kind of thinking about, was basically droplet spectral dispersion, the width of the droplet spectrum, and that's because it has some impact on the aerosol indirect effects. We know the Toomey effect, which is one of the impacts, but then if the spectral dispersion changes, then it's not exactly the way the Toomey envision it. There's an additional effect, which is called the dispersion effect. So if you look, this is just an example of some of those results. So with aerosol concentration, the number of cloud droplets typically increases, but you can see there is a lot of scatter, probably similar to one of the previous diagrams. This is this relative dispersion, which in these observations that you can see, there is clearly an increasing trend with the increasing aerosol concentration, which means increasing droplet concentrations and, of course, decreasing droplet sizes, the effective radius here. Perhaps an interest, it is interesting to point out that this is the diagram that I highlighted on the previous slide. So this is aerosol concentration, this is CAIPEEX clouds, the increase with the aerosol concentration. But if you look at the pie chamber observation, there's actually the trend is reversed. The increase of droplet concentration leads to small but noticeable decrease of this relative dispersion. So anyway, so this tells you how complex clouds are, and also tells you, which is probably relevant here, that pie chamber is a little bit different or quite different from natural clouds. So that's perhaps a point worth making. Now, continuing on this width and characteristics of those clouds, there was another paper that Tara was involved with, showing basically pre-monsoon clouds and monsoon clouds. And you can see narrow spectra peaking at relatively small diameter, and then monsoon clouds where they are kind of extending towards larger sizes. And then, of course, more analysis, more data on the bottom panels. Here, you get the same kind of pre-monsoon, 2 cases, 3 monsoon cases. Now it is structured by the adiabatic fraction, and it kind of behaves as you expect. For example, when the adiabatic fraction is large, so it will be somewhere here, then there is not much dilution. The mean radius is large, and then, of course, when it's dilution, then the radius gets down. And again, spectral width at the bottom. I don't have spectral dispersion here. So in other words, spectral width divided by the mean radius. But you can see that there are some observations that can kind of guide our modeling efforts, if you like. So that's something that we need to keep in mind. Now, Sachin actually showed that paper, and I really like that paper. And in fact, I was the JAS editor when it went through, and I was very happy to help this paper published. Sachin didn't stress this, but it's really, if you think about it, it's really an impressive simulation, because this is a simulation of a large, very large area, and actually quite extended time, like, I don't know, 28 hours, but it's using spectral microphysics. So it's really, and it has been done a few years back. So it's really a kind of tremendous effort to get a simulation like that done. So this is the area when there were aircraft observations, and in fact, one of the biggest advantages of this study that Sachin already explained to you in more detail, that I want to do it here, is that all those kind of complicated observations with different instruments, they were kind of merged to kind of show what's going on at different temperatures, different heights, so on and so forth. And then it was actually compared, those observations were compared to simulated characteristics with updrafts and within downdrafts. I don't think we have enough, and not talking about Indian community, but generally the overall the community, the cloud physics worldwide cloud physics community, we get enough those kind of comparisons between observations, really sophisticated observations with really sophisticated simulations using bin microphysics. So this is really interesting and worth pointing out. Now, of course, I wouldn't give this talk unless I talk a little bit about the invigoration. That's something that Hugh Morrison, myself, and other people have been working on for quite a while, maybe a decade. The point is that because those dramatic changes in aerosol conditions between dry pre-monsoon and polluted conditions and wet monsoon conditions, Indian subcontinent seems like an ideal place to study hypothesized convective invigoration in polluted environments. What I mean by invigoration is the increase of updraft strength due to pollution through cloud microphysics. And of course, you know what is coming is this paper that Danny Rosenfeld put over a dozen years ago, which I often used to show. And of course, the title that suggests that you can go from flood or drought just by aerosols, changing aerosols, which is of course complete nonsense. But anyway, you know, the journal, one of the tabloids of what we do. Sorry. And for those of you that don't know this figure, this is a very nice figure that basically shows hypothesized differences between polluted at the bottom and pristine. Those dashed line is a 0 degrees level, and this paper argues, and of course many after that picked up this theme, that in the polluted environment, warming processes will not be very effective. You will move water into the upper troposphere above the freezing level, and then when it freezes, then it gives convection extra kick. And Rosenfeld was not the first one who hypothesized that. There was another paper, I think Danny was involved in that paper a few years earlier over the Amazon, when they look at convective clouds over the Amazon, and that's where this kind of a conceptual picture came about. So the key point is here, this invigoration, and we asked the question whether this invigoration is possible. And if you do the math, the argument is that it really should not be possible, that this is basically somebody who doesn't understand cloud dynamics well could think about this, because if you think about density potential temperature, which is basically what drives cloud buoyancy, that depends on the potential temperature, what the vapor and condensate. And the argument is, according to their argument, that if you carry water across the freezing level rather than kind of offloading it below freezing levels through precipitation, when it freezes, it will give you extra kick because it will change temperature. However, if you do the math, basically do the perturbation density temperature, which depends on the perturbation temperature and perturbation mass that you carry, this cloud water now changes is Q. And the argument is that if you freeze it, that's the amount of heat that you can get, or amount of change of the density potential temperature. But then carrying it also, of course, you pay the price on the buoyancy. And these two are basically comparable. Not exactly, and you can argue that some details matter and this and that. So our argument was from the beginning that this invigoration is not possible. But anyway, it's interesting that in this paper, which Sachin did quite a bit of explanation about, they actually ran CCN with 100,000 and 3,000. And as already Sachin pointed out, over the entire domain, the difference is small, but again, the convection is parameterized over the entire domain. There is some, clearly not drought versus flood, but there is some change from in this inner domain by going into higher resolution, higher CCN concentration. So you may say, okay, so there is some invigoration. Well, the problem is that this is just one simulation. And if you look at in this paper at some other statistics, this is, for example, vertical maximum updraft statistics as a function of time and as a function of height, you basically see that there are different realization of convection. So the point is that, yes, there is something going on inside those domains, but it's mostly different realization of convection. And if you look at the vertical velocity statistics at different temperatures, 5, -10, and -20, you can see that actually, if there is an invigoration, you should see more high vertical velocity for 3,000, and it's actually the opposite. If anything, that's the opposite. But the point is that these differences are not statistically significant. So that paper, is intriguing, but you have to be careful because you're changing CCN and you're basically changing the realization. So, for example, you should do something like piggybacking for this case, or you cannot argue because one simulation is not enough. You should have an ensemble of simulations, and then maybe you could be able to kind of argue about those differences. And of course, there are other papers that we've written. Recently, we had an exchange with Jiven and Alexander, so there was exchange in JAS published earlier this year. So if you're interested into kind of reading more about it, do it. If you are tired of the subject, as I am, I can tell you that, just disregard. Now, the final few minutes, I would like to talk about this another aspect that I think is highly relevant and highly important for the CAIPEEX project is the education of new generation of Indian scientists. So I'm pretty sure some of the people in the audience will be embarrassed by what I will show. But these are three young Indian scientists. So there is Neelam Malap, there is Sudarshan Bera, there is Lois Thomas. I worked with three of them, I have to say, and I'm very pleased to see that they are still around. They kind of are developing themselves, making some progress. So let me show some papers and some outcome of their projects. This is a paper that Lois wrote and I helped, and Neelam is also there, of course, Tara is there. It was a very simple project that resulted in a kind of a really good journal publication. That's what Lois did, basically analyze pre-monsoon and compare it to monsoon soundings, looking at things like CAIPEEX. Lois was then undergraduate, so this was really her kind of a first cloud physics science, relatively simple, but the results were interesting, and I think we, together with Tara, we built a good story out of it, and it ended up in a good publication. So this is another paper that Sudarshan wrote with Tara, basically looking at the entrainment rate and behavior of convection when you change relative humidity. So I'm showing one of the pictures from that paper. So the relative humidity was changed from 80 above the mixed layer, if you like. So something like 1.5 kilometers, maybe 2 kilometers, was reduced from 80 to 50%. And kind of run into the equilibrium, and what the outcome is, which is perhaps not surprising considering that studies like that and arguments like that are in the literature since basically at least 20 years, I would say almost 20 years, is that basically when you get less humid environment, the convection kind of doesn't reach as high as when you have a humid environment. And we kind of expect what's the reason for that is entrainment and mixing, cloud losing buoyancy more easily when you get low humidity. So that's a nice study, basically kind of supporting this earlier studies. Finally, Nilam has a poster in this conference, which I took and copied, which is basically running the cases for this CAIPEEX cloud modeling workshop case, which is a diurnal cycle. So prescribed surface fluxes, those different domains that the data comes from, and so on and so forth. So a relatively simple study looking at cloud fraction. Of course, nothing happens. Then you get convection because surface fluxes go up. And there are some differences. So you may ask, is that really because of different aerosols? And this is very simple parameterization, so I would be surprised, or just different realization. So maybe ensemble is needed. But that's basically why I really believe the CAIPEEX, you can see the symbol here, it's really plays role in the education of new generations. So I finish with this slide. As I said, Tara asked me to give kind of general overview or kind of context for this case, and I thought that this is what has to be stressed, that this is the Indian government project. The Indian government is paying for it, but it moves science. There is no question about it. It develops infrastructure, research infrastructure. I already mentioned that, and if you would like to know more, ask Tara how many efforts, how many years of work it resulted in having aircraft and all the places to do even more advanced research than at the beginning. And I think the key is that there is a new wave, new flood, if you like, maybe not flood, but there are new scientists that are involved, and of course we know how important environmental change and climate change, and we don't know what will happen to clouds in the future climate. I mean, we have there are already some kind of thinking of what might happen, but it's important to keep those people engaged and keep them in this cloud science, if you like, because clouds are important for climate and climate change, and locally, like over the Indian subcontinent, but also globally, because if we go the way we're going right now and we do nothing, then of course our children and grandchildren will be in trouble. So that's my talk. Thank you very much, and I'm sorry if I disappointed you not talking about specifically some results from the field project, but that's how I kind of thought Tara wanted me to do. So this is my few cents to this case. Thank you very much.
Yeah, thank you, Wojtek, for delivering this nice talk and highlighting the importance of CAIPEEX to this workshop. And I'm very much thankful for this talk. And now we are open for a few quick questions on this talk. So,
Sudarshan?
yes.
Yeah, there are hand raised, please.
Yeah.
Professor Sayajit, I think you are spotlighted. You can unmute yourself.
All right. Thank you so much. I was quite amazed at the depth of research that you did with Tara and Sudarshan, and thank you for pointing out the young contributions. I have two small specific questions. The first is about, to what extent does invigoration smear the gradients of pollution, particularly over Indian cities? So if you have a lot of invigoration, is it going to have, it'll smear the pollution completely from lower down to top up? That's the first question. That's important for various health issues. And the second question is, have you looked at how invigoration might impact the dispersion parameter of condensation nuclei?
So first of all, I was trying to make a point that I don't believe the invigoration happens. However, your questions are important because, of course, if convection happens over the city more readily than over the outside the city, and there are some reasons why this might be so, because of course surface heating is different over the city than over the let's say fields outside the city. Then, of course, the transport of pollution, which invigoration, whether with invigoration or without invigoration, that's an important aspect. And I think I expect that there is quite a bit of work going on trying to understand. I know, for example, that Koreans have a project that kind of looks at gradients of pollution actually affecting convection. So it's not necessarily invigoration, but just having a gradient of pollution near the cities, which affects, for example, the surface heating, the heating within boundary layer, and also within free atmosphere. And I know that they're looking at those effects, or have looked at those effects at some point. So yes, gradients of pollution is something that affects convection independently. And I know, for example, that some of those people that believe in convection invigoration are looking at those kind of effects using more sophisticated model, including bin microphysics, but also with aerosol prediction. So it's Wolf Chem, as we call it at NCAR, Wolf with chemistry.
Yes.
They're using it in the Houston area, which is kind of a really industrial place when a lot of gasoline is being produced. And then plumes of pollution affect convection around the city. So yeah, there is actually a project that is about to start, I think, in fall, looking at convection and aerosols, around the Houston area. I don't remember the acronym, but it's an important problem. I agree, and I appreciate the question. But that's kind of a little bit to decide what I was talking about, but certainly something relevant for mega cities around the world, for sure.
Yes. Thank you. And the second part, basically, does invigoration affect the dispersion of condensation nuclei at the cloud base significantly?
Well, if it happens, convection, of course, impacts the CCN, but whether, and probably more through the updrafts and downdrafts, more through the downdrafts and cold pools, they're spreading, sweeping, if you like, the area from pollution. But that's something that I would hesitate to comment or speculate. But it's something that probably is quite important, I would think. But leave it like that.
Thank you so much. Thanks a lot.
You're welcome.
Sudarshan, may I say something?
Yes, madam.
Yeah. Thank you, Wojtek, for giving an overview of CAIPEEX by taking everyone through this. And really, we are all grateful to you for all the goodness that you are showing us. And definitely for this, the last point that you mentioned about the education of new generation of scientists, that is why we are wanting to do this ICCP and the workshop, because this will generate new interest and new insights into the minds of people. And
Yes,
I believe that. Yes.
No, I just wanted to say that it's really, really a pity that we cannot be, this pandemic, put all of us into kind of a difficult times. But I think especially you and people in Pune who work so hard to have this meeting there. And of course, that I really supported you in this proposal to have it there. And then this misfortune happened, and it's unfortunate. So I hope we will do something in Pune related to cloud physics. I'm not sure as a cloud modeling workshop. We know that I think the next ICCP will happen in Korea. I think this is already decided. So probably workshop will happen in Korea. But anyway, some cloud physics related activity, kind of not to replace, but add to this kind of internet-based workshop would be really good. So I'm pretty sure we may talk about it, how to do it and when to do it.
Definitely.
Anyway.
Yeah, definitely.
Thanks,
Thank
Tara.
you.
Thank you.
Thank you for your insights, and it will definitely give opportunities to think about further. And I also would like to give open invitation to anyone who is wanting to have collaborations with the CAIPEEX. Please talk to anybody, any one of us, and please come forward. We are ready to collaborate now. Actually, after the conference, we will get more time, and right now we are a bit occupied with the conference, and previously we were busy with our field campaign. So, but now we will come out from all of that.
All right.
Thank
Thank you very much.
Wait, Jack, could you unshare your screen?
Unshare my screen. Oh, I don't know how to do it.
There is, I think, another question.
All right, you unshared it already.
Okay. Mahan had a question, I think. Or maybe not. Maybe he gave up.
Yeah, I spotlighted Professor Satyajit Ghosh. So he's having a question, I think.
Yeah, I think we don't have any more questions. Sudarshan, you can move forward with the agenda.
Yeah, I think as per agenda, we have now a break for 10 minutes. So we can resume after that.
Great, thank you.
Oh, there is one hands up from Madhu. So
Yeah, you're spotlighted.
And we would like to thank Tara Madam to bring this conference and have exposure to the great cloud physics modeling and things. Thank you very much, Madam. From you have been working for it for last 4 years and telling at different places to attract more people to come here. And thanks for bringing to India, and we have a great chance to expose and see the great guys who are working in this cloud modeling things. Thanks to Tara Madam and his group, and also Grabaski sir for helping to come to this one into India, and he's also proposing one more online conference for the cloud physicists in India. Thank you very much, sir. We look forward for the radar based some studies on the cloud physics. Thanks to Tara Madam and Grabaski sir. Thanks.
Thank you, Madhu.
Yes, ma'am. It's my pleasure. Dhanyawad.
okay, so we'll have break now and we'll resume in 10 minutes.
Hi, Dr. Sonia. Hello. I am good. I am good. We had a slight glitch yesterday night.
And then mine went off. Yeah, you were saying This happens. So I
Yeah, we are ready to resume now. So, this is the agenda for next lectures. So next, I'll be presenting the summary of all ongoing works from this case study, and then thereafter there will be a talk by Dr. Onurose from NCMRWF, and then the session will be open for question and answer, and then there will be a discussion on future plans. Can everybody hear me?
Yes, sir. Yes.
Okay, so I will share my screen. Okay, so welcome back to all. My name is Sudarshan Mehra, and I work at IITM. And I am going to present overall work, overall result from the case study. And these results are contributed from different members, which are listed below. Dr. Onurose, Dr. Jaikumar, Dr. Adrian Hill from NCMW and UK Met Office, and then contribution from myself, then from Dr. Gayatri Kulkarni from IITM, of course Sachin is there, and then from Neelam Rajput SPPU, then from Neelam Mala from IITM, then Janani from Aizar Pune, and Somu from IITM. So this is the summary of the case study. So in this table, I have listed various model people has used, and domain size and CCN condition, runtime, and microphysics scheme, and how they are initializing their model. So for me, I have used WRF LES model with bulk microphysics scheme, WDM6. Model is for 30 kilometer by 30 kilometer domain with 100 meter resolution. And CCN I have used 100, 1000 and 3000. Runtime is 8 hour. And next is Monk mod LES model by Onurose et al. From NCMRWF. And they have used 20 kilometer by 20 kilometer domain with 200 meter grid size. And they have also used 100, 1000 and 3000 CCN, and they run for 10 hours. The microphysics scheme, they have used Kasim double moment scheme, and they have used radio sonde as well as D1 and D2 sounding. Then work by Neelam, she has used baby Euler model from Inkar, and that model is for 30 kilometer by 30 kilometer domain with 500 meter resolution. And she has used instead of CCN, she has used doublet number concentration 50, and she ran for 24 hours with Berry microphysics scheme that is having simple warm rain process and simple ice process. And she used D1 and D2 sounding for the model. Then model run by Gayatri et al. They have used WRF alias Bean microphysics with this Huji microphysics scheme, Kane et al. 2009. And then they used two CCN cases, 100 and 3000 with 6-hour runtime. And they initialized their model by radio sonde. Then Neelam Rajput et al. They used WRF CRM model with bulk microphysics, and model domain is 100 by 100 kilometer. CCN is 1000, runtime 8 hour, and she has used 5 microphysics schemes that will come later, and she initialized by radio sonde sounding. Then Somo et al. They have used WRF alias, and he compared bulk and Bean microphysics. He used 20 by 20 kilometer domain with 200 meter resolution, and CCN is 100. And he used bulk microphysics, that is Morrison scheme, and Bean microphysics, that is Huji microphysics scheme, Kane et al. 2009. And he has used radio sonde sounding for model initialization. And Janani et al. They have used WRF CRM model with bulk microphysics with 100 by 100 kilometer domain and 1 kilometer resolution. And she has used several CCN conditions from 200 to 5000 with WDM6 microphysics scheme and initialized by radio sonde sounding. Okay, so there are various objectives for this case. First objective is to understand the sensitivity of environmental moisture content. That objective is carried out by myself and by Gayatri. And next is sensitivity of CCN on cloud and rain. I think that is a common objective for all the case participant. And then sensitivity of sounding like D1 and D2 domain, that is done by Anuroj and Neelam. Then sensitivity of Bean and bulk microphysics in CAIPEEX convective cloud, which is done by Somo et al. Then sensitivity to wind speed. So this is done by Janani and others. Then sensitivity to PBL scheme by Neelam Rajput. She has used two different PBL scheme, and she tried to investigate the effect of PBL scheme on the cloud development. Then there is another study to see the sensitivity of auto conversion microphysics in the WRF model. This is the study done by me. This is to investigate the entrainment rate and mass flux under different environmental humidity condition. So I have used alias model configuration with ideal run using radio sonde sounding, and domain is 30 kilometer. Cloud domain top is 20 kilometer, and DXDY is 100 meter. DZ is stretching grid with close to cloud base, it is 50 meter. Then microphysics scheme I have used WDM6 bulk scheme, no radiation scheme. There is a damping layer at the top of the domain, and boundary condition is double periodic. So simulation setup, I have 5 simulation run. One is the default sounding from the radiation observation with 100 CCN case. And then I have dried the sounding with 10% and 20%, so 2 dry case, and I'm using CCN condition 100 for both. And then I have run 2 polluted case. One is 1000 CCN and another is 3000 CCN with the default sounding. So this is my model initial setup. So this is potential temperature, you can see on the left, and middle it is the wind speed U and V. And on the right, you can see the water vapor mixing ratio. So this is water vapor mixing ratio is changed for 3 different run. One is default run, another, and there are 2 dry simulation, 10% and 20%. And you can see the cloud development. I have there is a dash line. You can see that is the cloud top height, and you will be amazed to see that the cloud top height is basically determined by the wind direction. So if you see the U component of the wind, that is the westerly wind during the monsoon, and the wind direction changes around 5.5 kilometer, and that is the cloud top height we are getting from the model. So wind direction actually plays important role for this cloud development. So this is my model cloud, just snapshot of vertical distribution of liquid water content. So this is left one is default, then middle is dry one, and next is dry two. So you can see that cloud fraction decreases significantly when we dried the system, and also cloud top height decreases as well as cloud base height lifted little bit up. So the main finding from this is decrease in cloud fraction and cloud depth with drying of the environment, and cloud base is lifted up in the dry environment. These are time variation of different model parameter. First one is accumulated rainwater at the surface. So this is for all the 5 simulation cases: default, polluted 1, polluted 2, and dry 1 and dry 2. And you can see that with the drying, when we dried the system, and the accumulated rain decreases, as well as the onset time of rain also delayed by drying the system. And for pollution effect, you can see the with polluted condition, total rain amount actually increases. And for liquid water path, there is slight increase in with pollution, but with drying, liquid water path decreases significantly. And ice water path, actually it is having a wave nature, and there is no clear trend, and it varies around 10 to 12. And so main finding from this study, the higher CCN produced enhanced accumulated rain, and drier environment decreases amount of rain and delayed the onset process, and decrease in liquid water path and ice water path due to drying. So coming to entrainment rate investigation. So here I have used the bulk approach of bulk plume approach, which is given by Bates 1975. So I am estimating the fractional entrainment rate using this equation. So here this phi is a moist conserved parameter that can be either water specific humidity or moistatic energy. So here I have used water specific humidity. This is a total water, and U refers the cloud sample with positive buoyancy or upward, that is upward moving parcel, and subscript E refers environmental quantity. So from this investigation, what I found, with change in CCN, that is polluted 1 and polluted 2, we do not see much difference in the entrainment rate. So entrainment rate has a very general pattern. So at cloud base, it is generally high, and it decreases with height, and it is like more or less constant for up to 3.5 kilometer, and then there is a sharp increase. However, when we dried the system, we see there is a change in entrainment rate, and the impact is more effective towards the cloud top above 3.5 kilometer. So with drying, we see the entrainment rate actually decreases, and this finding is also similar to the reported work by Bera and Prabha 2019 in JJR. So we are getting inline result. So on the bottom panel, I have shown total specific humidity and particle profile. So on the dash line, it is the environment, and the solid line, it is for in cloud sample. So you can see that in cloud sample, it decreases with height, and it is like a parallel to the environmental sounding. So there is a entrainment throughout the layer. So this is basically the lateral process of entrainment, where dry ambient air mixed from the lateral cloud edges, and then they diluted the conserved parameter. And it can be noticed that towards like some I have highlighted by a circle close to 4 kilometer, where you can see there is a rapid decrease of the in-cloud moist conserve parameter, and that leads actually high entrainment rate, which is shown on the upper panel. So the main finding from this is that polluted cloud doesn't show sensitivity to entrainment rate, but dire environment leads decrease in fractional entrainment rate. So moving to next slide, here I have shown cloud core mass flux and cloud fraction. So these are all 5 simulation cases: dry 1, dry 2, polluted 1, polluted 2, and default case. So you can see a significant change with dry. So cloud fraction generally having a bimodal shape. One peak is there just above the cloud base, maybe 1.5 kilometer. Then it decreases, and then there is a higher peak close to 4.5 kilometer. And you can see there is a significant change due to drying. So with dry condition, cloud fraction decreases. However, for CCN changes, there is no such significant impact on cloud fraction. And similarly, we can see the mass flux. So on the right side, I have shown the mass flux, and you can see a mass flux also similar to the cloud fraction. It shows a decrease with the drying. However, for different CCN run, there is no significant change. So now on the bottom panel, I'm showing in-cloud updraft, and for dry simulation and for polluted simulation. And we can see that with drying, we are getting higher in-cloud updraft. But for CCN run, there is no significant difference. So that this higher in-cloud updraft, it can be also related to like lower decrease entrainment rate. So so if there is a decrease in entrainment rate, cloud will get more updraft, and they'll be more stronger like updraft velocity. So the main conclusion from this, cloud fraction and mass flux have a bimodal shape with height, and cloud fraction and mass flux do not change with varying CCN but decreases with drying. Cloud core updraft is stronger in dry case. So these are a summary of my study. So from LES of CAIPEEX convective cloud simulation, we are getting different dry environment was carried out with bulk scheme, and drier environment decreases total rain amount and delays the onset of precipitation process. Drying of the environment decreases cloud fraction and cloud depth. Drier environment also decreases fractional entrainment rate. Higher CCN produced enhanced accumulated rain, but cloud depth and liquid water path are mostly similar with the default case. Polluted cloud doesn't show sensitivity to entrainment rate, and the cloud fraction mass flux have a bimodal shape with height. Cloud fraction and mass flux do not change with varying CCN but decreases with drying. So, and the cloud core updraft also changes with dry to moist condition. So we'll move to the next study done by Gayatri Sachin and then their colleague. So they have investigated precipitation formation in different thermodynamic aerosol environment over Indian Peninsula region using beam microphysics scheme. So this is their model setup. So their model is like a LES model, 20 kilometer by 20 kilometer domain with 200 meter resolution, and model top is 15 kilometer with double periodic boundary condition. Time step is 1 second, and duration of simulation is 6 hours, and output is taken at every 2 minutes. And microphysics, they have used SBM spectral beam first version, KNATL 2009 and 10, and they have varied mixing ratio like from -20 to +20. So it's, this control is the default sounding, and they have decreased by decreased by 20%, 10%, then increased by 10% and 20%. And CCN condition, they have used two different CCN. One is 100 and another is 3000 as the proxy for clean and polluted condition. So this is their different simulation run, and this is the sounding on the right side. You can see it is already discussed by Sachin at the beginning of this session. And okay, so I will move to the next slide. So this is also shown by Sachin during his presentation. So this is like combined effect of moisture and aerosol. Just to summarize, I am mentioning that with increase of water content, that is -20 to +20, there is a positive correlation with various in cloud parameter like supercooled liquid water, ice water, snow water, or Gropel water. And so there is a positive trend, and the effect is more severe for the polluted condition, which is presented by this red line. So their main finding is more dramatic impact from moisture compared to aerosol pollution. So this is the summary for summary of the study. So positive correlation of various cloud water with moisture content, higher precipitation with increasing moisture or humidity. Then higher CCN produces enhanced rain in moist condition. Documented process rates with bean microphysics, and importance of halite Mossop process is investigated. And finally, the impact of moisture is more dramatic than CCN, which is already mentioned. So now I'll move to the next study done by our NCMW people, Onurose, Jaikumar, and Dr. Adrian Hill. So their objective is to understand the aerosol cloud interaction during CAIPEEX case study. So they have used the model LES model, Metopis NERC cloud model, that is MONC, and they have initialized using radiation day. Then they have also taken D1 and D2 sounding with different CCN condition. So this is their model setup. So 20 kilometer by 20 kilometer domain with 200 meter and 50 meter resolution. So simulation period is 10 hour. Cloud microphysics scheme, they have used Kasim double moment scheme, and they have used radiation scheme. So this is result from their simulation. Vertical. This slide shows vertical profile of cloud microphysics parameters like water, rainwater mixing ratio on the left, and then liquid water QL is liquid water mixing ratio. And these profile are plotted for two different time. That is for 3 hour of simulation, and on the right it is for 7 hour of simulation. And this is on the left, it is total cloud fraction, and next one is liquid cloud fraction. So you can see the difference for different CCN run. So CCN 100 presented by the green color, and you can see the CCN 3000 which is presented by this black line, and you can see a significant difference. So rainwater is they are getting more rain for low CCN condition, which is kind of opposite to the previous war. And you can see the liquid water mixing ratio. She is getting high liquid water content for the polluted case, but she is not getting the higher rainfall for the polluted condition. And the trend is similar for the 7 hour. However, the amount of rain and liquid water content, I think it decreases compared to 3 hour. So on the lower panels is plotting the total cloud fraction. So you can see a bimodal shape of the cloud fraction, and for total cloud and total cloud fraction and liquid water cloud fraction. And cloud fraction also like it is increasing for polluted condition compared to the CCN 100, that is the clean condition. So these are time evolution of model different parameter. First one on the left, you can see the rainwater path. On the right, you can see liquid water path. And on the bottom panel, you can see the ice water path. And this is only ice hydrometeors. And on the right, it is that all types of hydrometeors from ice process, like ice, Gropel, and snow. So on the top panel, top left panel, we can see there is a decreasing trend. So the rainwater decreases with increasing CCN number, and also it if you also it delays the onset of precipitation for the polluted case. However, you will see it is quite different for liquid water path. Liquid water path actually increases for higher CCN compared to the clean condition. and also the peak is slightly delayed compared to the clean condition. Similarly, ice water path also higher for high CCN case. We'll move to the next slide. So this is the summary slide of this work, and I have to mention that the next presentation will be given by her, so you can have more result from her work and discussion. So main summary from this study: enhanced CCN delays the onset of rainfall, while CCN 100 generate quick and intense precipitation. Cloud fraction exhibit a clear bimodal structure. Liquid water path and ice water path increases with higher CCN. So moving to the next study done by Neelam from IITM. She is looking at diurnal cycle of convective clouds of the CAIPEEX case and effect of the various sounding. So model she has used which is baby Euler model, and domain she has used 30 kilometer by 30 kilometer with 500 meter resolution, and time step is 3 seconds. So you can see the various soundings she has used: relative humidity and potential temperature. So you can see the like a D1 domain and D2 domain, there is quite a difference in relative humidity. However, potential temperature, this is the difference in potential temperature compared to the default sounding, that is D100. So these are just a few results from her study, and she has given a poster on her study. You can go there and have discussion with her. So more information is available there. So from her study, just to show the diurnal cycle of accumulated rain rate, that is millimeter per hour. So you can see the maximum peaks is getting around the afternoon time, and there is a difference between domain D1 and D2. So she is getting more rain for domain D2 compared to D1. And however, for liquid water, liquid water she is getting more liquid water for domain D1 with high CCN, and rainwater also it follows similarly. So she is getting more rainwater for the domain domain D2 with CCN 1000. So the key finding from the study: higher CCN and domain D2 thermodynamic. So she is not using any CCN sensitivity study here, but she has used the domain D2 domain, which is coming from different CCN run, which is originally done by Gayatri et al. In 2017. So the main finding is high CCN and domain D2 thermodynamic shows deeper convection up to 12 hours, and most ice water and rainwater is seen in the higher CCN thermodynamic case. So moving to the next work done by Somo. He's from IITM Pune, and he has also given a poster, so you can get the details of this work. So main focus of this work is comparison of bean and valve microphysics using WRF LES simulation, and model setup is given here. So he is using a domain of 20 by 20 and 6-hour run with a radius on the sounding. So for bulk microphysics, he is using Morrison scheme, and for bean it is Huji scheme. So he has used a constant CCN of 100 per cc. So here these are the model results from his study. So he is showing maximum reflectivity, column maximum reflectivity, and on the top it is from bulk simulation, on the bottom it is from bean simulation, and you can see there is a huge difference in cloud organization. Clouds are more widespread and organized for the bean simulation, but for bulk clouds are more like localized and deeper. So there is a significant morphological differences that are noted in the two simulation, and bulk I think that is done. So moving to the next slide, here we are showing the effect on precipitation from these two simulation, bulk and bean. And you can see on the left it is like a special distribution of accumulated rain, and on the right panel I am showing the time plot of total rainfall. So for bin microphysics, SBM, he is getting more rain compared to the bulk microphysics. And from the spatial plot, you can see the rain is more like widespread and organized for the bin microphysics scheme. Okay, so moving to next work, which is done by Janani Sri R from IITM Pune. And she has also put a poster. You can visit there and get details. So main focus of this work is to investigate effect of wind shear and CCN using WRF CRM model. So this is the model configuration, WRF CRM with 100 kilometer by 100 kilometer, and runtime is 4 hour. Microphysics scheme is WDM6 class. Then she has used I think ISU PBL scheme, and she has a different CCN setup from 200, 1000, 3000, and 500, 5000. And for wind effect of wind shear, she has changed the wind velocity like a default. Then there is a half wind, and then there is a zero, that is there is no wind speed. So you can see the sounding like wind vertical profile of wind speed U and V. So there are two cases. One is the default wind by the solid line, by the dash by the solid line, and half wind, which is presented by the dash line. So these are a few results from her model simulation. So on the top, we can see this is a profile of liquid water content and gram per meter cube. And you can see that for different wind, there is a default, then there is a half wind, and there is a no wind. No wind I have highlighted by black circle, you can see. And actually for no wind case, this is the green line. You can see this cloud depth. Cloud depth is quite low, as well as liquid water content is getting less compared to the default simulation. And for CCN case, actually higher CCN also decreases liquid water content slightly. And same thing is also presented like effect of wind on the lower top panel, and effect of CCN and on the lower bottom panel. So the main summary of her study: wind shear has a vital role in the dynamics of monsoon convective cloud, and cloud depth and liquid water content decreases when wind speed decrease. Higher CCN decreases liquid water content slightly. She has not investigated, I think, rainwater. So moving to the next work by Neelam Rajput, and she has investigated autoconversion parameterization in monsoon convective cloud, and also she is looking sensitivity of PBL scheme in WRF model. So this is the model setup. She is using 100 kilometer by 100. Actually, she has used two different model setup. One is 100 kilometer and another is 400 kilometer. And PBL scheme, she has used two different PBL. One is MYJ scheme, and another is ISU PBL scheme. And she has also used 5 different microphysics scheme, which is listed here with both. She has run model with both PBL scheme. So moving to the next slide, here we can see the model result. So this is on the top, we are showing vertical profile of cloud water content, and on the right side it is the liquid water content. And she has compared these dot symbols. Actually these are observation from hot wire probe and fast forwarding spectrometer probe. So the model, this is the top panel. It is for the MIJO PBL scheme, which is actually underestimating the liquid water. You can see there, observed liquid water is quite high compared to the model simulated, and for all the microphysics scheme. However, when she changed the microphysics scheme and made a smaller domain, 100 kilometer by 100 kilometer with ISU PBL scheme, liquid water content, you can see for the 3 microphysics scheme, liquid water content is overestimated, and two microphysics scheme, it is more or less like it is more close to observation or bit underestimated. So she has also put one poster there. You can visit there for more details. So the main summary from her study: cloud development is sensitive to PBL scheme. For issue PBL scheme that generates a deeper cloud than meso PBL scheme, and effect of dispersion parameter with autoconversion rate and precipitation has been tested, which I have not presented here, but you can visit her poster and more details can be available there. So this is my summary of all model result, and on the top this is similar to the my first slide where I was comparing different models. And so on the top you can see different model: WRF LES, bulk, monk model, then baby oiler, WRF LES bean. So these are the different model used by different members. And on the left you can see domain size, CCN, runtime, microphysics scheme, and two different parameter is added here. One is cloud top height, and then there is a remark column. So this remark is mostly like how aerosol is affecting on precipitation. So, so already model setup I have discussed. So just two things I will discuss here: cloud top height. So cloud top height in most of the model, actually cloud top height is around 5.5 kilometer. So these are like mixed phase type cloud, and only two different model like baby oiler bulk simulation, it is generating a much deeper cloud, 10 to 12 kilometer. And then there is another simulation done by two different PBL scheme. For issue PBL scheme, however, simulated cloud is reaching up to 8 kilometer, but the other PBL scheme is close to 5.5 kilometer. So these are main point. And so for rain enhancement, the WRF LES bulk simulation, I have seen there is increase in rain for high CCN. For so NCMRWF Monk LES model, they have actually they are getting opposite response. So rain is decreased with CCN. However, they are getting higher liquid water path and ice water path. So this is quite interesting that they are getting more liquid water and ice water, but model is unable to make higher rain. And then other model like baby oiler, it is agreeing with like high CCN. So she has not used CCN simulation, but different CCN sounding, and that is generating higher rainfall. And then WRF LES bean microphysics done by Gayatri et al. They are getting also more rainwater for high CCN. And then for this PBL scheme sensitivity study, actually she is getting main remark is that issue PBL is better than the meso PBL scheme, so which is getting reasonable cloud depth. So comparing bean and bulk microphysics by Somo et al., he is getting like bean. The main remark from the study is that bean microphysics is producing more rainwater than the bulk microphysics. And WRF CRM model also is getting a slightly decreased liquid water content, although there is no result from the rainwater. So I think that's all from my presentation. And now I open the session for questions.
Yeah, Sudarshan, by the way, you gave a very nice overview. So many different results, and
Yes,
it's
yes.
amazing to see investigation on so many different aspects.
Yes.
And I think there's an interesting trend that can be found from your results. Are it seems like environmental condition, or at least dynamics and thermodynamic variables or conditions,
Yes.
may overpower the influences of aerosols and CCN.
Yes, yes, yes.
Yeah, so it's quite evident that this is the case, at least for your case discussion. So yeah, thank you for the great discussion.
Yeah, thank you, Lulin.
Yeah, if anybody have questions, please raise your hand and I can spotlight you. All right, here we go. Chunzong, you are spotlighted. Unmute yourself. Chunzong, are you ready?
Yeah, I was trying to find how to
Unmute. Okay. Okay. Go ahead.
I'm sorry.
Yeah.
Okay, thank you for your talk. I have a question about entrainment rate. Can you go
Yeah.
back to the slide showing the vertical profiles of entrainment rate under different conditions of relative humidity?
Yeah. Can you see my screen?
Yes.
Yes, I can see it.
Yeah. Yeah.
The vertical profile. Yeah. So it's a conclusion here. Drier environment leads to decrease in fractional entrainment rate.
Yes.
But I think this is only valid for the upper part of cloud.
Yeah. Your
Like
voice
about
is breaking.
3.5 kilometers, right?
Your voice is breaking. I'm not getting your voice properly. Yeah. Can you repeat your question? Hello.
Chunzong, can you repeat your question? Because you were a little bit broken off.
Okay.
Oops, still. Yeah, we couldn't hear you, Chunzong. All right. Maybe Chunzong has some technical difficulty. If you figure out your microphone will work correctly, we'll bring you back. Let's move on to next question that Jason Milbrand. So Jason, you are spotlighted. Yes.
Hello? Can you guys hear me okay?
Yes, I can hear you.
Yeah. Okay. Last time I spoke, I found out later nobody could hear me. I just wanted to, really interesting case and nice summary, by the way. I like the presentation. I just wanted to make a sort of a general opinion comment. With deep convection, of course, grapple plays a huge role. And one sort of concern I have with these types of studies is I feel that the role of grapple in the model simulations gets sort of overlooked. And in my opinion, the treatment of grapple in the microphysics schemes, whether it's bin or bulk, is going to play a large role in the signal that you get and whether or not you have high CCN or low CCN. And I'm not talking about ice nucleation. I'm talking about 4 droplets. If the microphysics scheme does not predict grapple density, for example, which has a huge impact on the fall speeds and vertical distribution and so forth, I submit for consideration that the signal that one would get by changing the CCN may simply be wrong. And I think that for these types of studies going forward, I think the treatment of grapple really needs to be focused on a bit more. Just a general comment and suggestion to the community.
Okay, thank you. Gayatri, would you like to give any comment to this? Gayatri is there?
Yes. So this is an interesting point, and it needs to be checked because we blindly usually consider that CCN directly impacts grapple, but grapple density also needs to be considered. So we will surely do this in our future works. Thank you.
Okay.
May I say something?
Yes, madam.
Yeah. Jason, this is a very nice comment from you. And what is the way forward you are suggesting in this regard? Because
there are
please.
Yeah, I mean, I guess I would say that the treatment of rimed ice, I mean, first of all, it needs to be double moment. If it's single moment, then it's just going to be the wrong signal. But I think that you need to have you can make the grapple density prognostic by predicting the volume mixing ratio. And if you do that, it allows you to parameterize the Rime density based on the droplet sizes. And so it takes into account then the very indirectly, but in a real way, the impact of the CCN on the evolution of Grapple. And so, there's a few schemes that do that already. But I guess my general point is I think that it's not. I think it's more important than people have sort of placed emphasis on. And I think there are ways forward. It's not, existing ways, techniques, even in bulk schemes.
Yeah.
All right.
Yeah, we move forward.
Wei-Chek has a question or comment. Go ahead, Wei-Chek. Unmute yourself.
I was frantically searching where is the button that I need to hit. I agree what Jason said, but I would like to remind, I don't have to do it for Lulin, but I have to remind other people that if you think the bin microphysics is a good benchmark for ice, the way those schemes are formulated now with this partitioning between cloud ice, snow, and grapple, I would argue that this is highly questionable just because the nature doesn't know where is the border between, let's say, snow and grapple. You go smoothly, through no rime, then a little bit rime, then a lot of rime, and where is the border? So there are other schemes that do it differently, one thing. And also there is Lagrangian microphysics that is kind of getting more and more popular. And we have quite a bit of experience with warm rain showing how bin microphysics provides some numerical problems comparing to Lagrangian. And of course, for the ice, we're working on it, Shima and others, Axel Seifert. So, but it's just a word of caution. Don't think that the bin microphysics is the end of the road and it will solve all the problems, because something like what Jason said, the grapple density is something that bin scheme probably assumes, doesn't predict. You can probably be clever and predict it, but that's not how things are done at the moment. So just a word of caution. And we actually had a paper that we wrote, Lillian was a leading author, which basically showed that if you just take off the shelf 3 different bin schemes, then and run one case with those schemes, then the results are different because there are so many details and every scheme does things a little bit differently. There are some assumptions, there are some ideas, and that has impact. And the squall lines simulated by 3 different schemes kind of look differently in each scheme. So that's kind of, you should keep this in mind, that the bin scheme is not the final word, and it's actually more problematic, I would argue, for some cases. So it's just a comment.
Yeah. Can I share my screen for about 10 seconds? Because I have that figure that Wojtek is talking about up, and I really think anybody who looks at bin schemes versus bulk schemes needs to look at this one figure from Lulian's paper.
Yeah, give it a try. I don't know.
I will not occupy too much time. If I can figure out how to do this, screen share. Because I think Wojtek's point is good. I put screen share. I'm not sure. Oh, sorry. I have to dark screen.
Yeah, you have to.
If I can't figure this out in the next 10 seconds, then I will.
Yeah.
Can you
give a try, Jason? And at the same time,
can you see this?
Not really. Maybe you should go to the speaker podium. Then you have permission to do it.
You know what? I don't want to occupy the time with this. It's a figure from a paper that Lulin wrote, and it's got 4 pictures. Well, 8. It's observations and 3 different bin microphysics schemes, and they're all dramatically different. And I think that's the point that Wojtek is making, and I think that's really is something that should be remembered. Anyway, but I just wanted to make the general point that the ice microphysics, the way ice is treated, and in particular Rhine, really it has a big impact in this type of studies about the effects of CCN. And I think that I suspect that gets sort of pushed under the carpet a little bit too much.
Thank you, Jason, for pointing it out. And Mercy, I think you are spotlighted. You can unmute yourself and ask your question.
Hello, am I audible?
Yes, we can hear you.
Yeah, probably my question appears stupid. Sorry for that. There are two questions. One is the study done by Soumya Samanda. You see the convection patterns totally different between the bin and bulk. Why is it? And the second one is, I think one of the study, what I understood was when the CCN increased, the LWC decreased, while in the other studies it was increasing. So, and why did this one particular study was showing opposite? Like, I think it means it is an anti-Toomey effect.
Yeah, Somo, you're there. I have spotlighted you. You can reply to Mercy's first question, why there is a difference in the cloud structure between bin and bulk microphysics. Somo, you're there?
Okay. Yes. Am I audible?
Yes.
Okay. Yeah. Actually, possibly this is because the representation of the ice hydrometeors due to the in the microphysics scheme. Now we know that in bulk scheme the hydrometeors are prescribed. Whether in bin scheme this is calculated or this is estimated due to the course of the model integration. So actually, in my poster, I have shown the mixing ratio plot. You please come and see there. This will give more clarification of your question. That we can see in bulk scheme the ice phase hydrometeors are not simulated properly, but in bin scheme it is simulated comparatively better. So that could be the possible reason because of this, and we know that because of this like widespread cloud structure in the bin scheme, because this bulks, these ice hydrometeors are mainly responsible for the stratiform counterpart, which I think is not properly represented in the Morrison scheme, which is the bulk scheme here. So this is the answer from my side. So hello, Mercy, are you there?
Yeah, I spotlight you, Mercy.
Yes. Yeah, thank you, Soumya. I'm sorry. I think the other study was from Neelam Rajput. I am sorry that I don't remember exactly who studied, but in the other one of the case studies shown, it was showing the opposite. That anti-Toomey effect was seen. So if anyone could enlighten me, why did that one particular study was different?
Yeah, I will suggest Mercy, you can visit her poster and there is more details about that work. So, or we can have the discussion during, there will be a question and answer session. So during that time, we can have this discussion.
Thank you so much.
So we'll move to the next lecture, which will be given by Dr. Onurose from ICMW. So, yeah, Onurose, you can start your lecture. I think you are already spotlighted. Yeah, you are spotlighted now. You can go ahead.
Okay. Hope you can see my presentation.
Yes, we can see.
Okay. Thanks, Sudarshan, for summarizing the results. I'll be giving a report of the CAIPEEX case study carried out using Monk model. Here are the participants. And coming into the CAIPEEX case study, these are the case study objectives from the organizers, and out of that we are focusing mainly on this aerosol effect on mixed phase cloud process and its impact on precipitation. And also we have carried out simulations using different initial profiles based on different domains. So our focus mainly on aerosol cloud turbulence interaction during CAIPEEX using MONK model. Coming into the LAS model, we used a MetaOffice NERC cloud model, which is a replacement of UK MetaOffice large AD simulation model. I just want to point out the two main scheme which we used for the present study. That's one, cloud microphysics is by CASIM. This is cloud aerosol interaction microphysics. It's a double moment bulk microphysics scheme, and it incorporates aerosol effects. And radiation in MONG, we have both options like LW, rad exponential, and Socrates. For the present case, we used Socrates, which is plane parallel radiative transfer scheme used in MetaOffice. Coming into the case study setup, we used a domain size of 20 kilometer cross 20 kilometer and vertically 19.4 kilometer. And the horizontal resolution is 200 meter and the vertical resolution is fixed and 50 meter. Cloud microphysics is by CASIM, radiation is by Socrates. And we have given surface boundary as a time varying fluxes. And simulation period is 10 hours. We kept a damping layer about around 17 kilometer. Lateral boundary condition is periodic, and the model initialization time is 5:30 UTC, is time, Indian time 11 IST. So mainly we focused on three sets of simulations. In the first set, we used initialization based on radio sounding and with different CCN values, CCN 100, 1000 and 3000. And second set, we used initialization and surface boundary based on the mean sounding data obtained from WRF D2 domain, which is 400 cross 400 kilometer. So it's like compared to radio sound, it's we felt like a smooth profile, and because it's obtained from a larger domain 400 cross 400 kilometer. And the third case, initialization and surface boundary based on mean sounding from D1 domain, which is 200 cross 200 kilometer of WRF. So by this, we thought to examine the variability in CCN by keeping environment same, and also by changing the initial sounding from different domain, how it impact. So this is like an evolution of the basic parameter. This is based on the radio sound initialization and domain average temporal evolution of the basic parameters. You can see that the diurnal variability is well captured. And coming into the cloud microphysics parameters, here again it's a radio sound initialization, and here three cases are CCN 100 is in the green color, and radio sound with the CCN 1000 is in red color, and radio sound with the CCN 3000 is in black color. And the x-axis is the time evolution, and y-axis is the different parameters. It's like integrated rainwater path, liquid water path, snow water path, gropal water path, and ice water path, and it's a total. This is already explained by Sudarshan. However, I just want to say that what we got while increasing CCN is, in all the cases we got rainfall quickly after 1 hour, and with the CCN 100 we got rainfall very quickly, and the intensity was high, and as the CCN increased, we got a delayed onset of rainfall, and the intensity was less. And so it's like but 100,000 and 3,000 case, three cases we have like a decreasing or increasing trend is there. Like here it's like a decreasing trend, and a liquid water path we could see a increasing trend. And other all shows like other parameters shows like a delayed peaking, and for example, Gropal in the high CCN case, and the magnitude is high for the ice water path. If we look on the total ice water path, also the magnitude is high. So we were thinking like about coast, this quick and intense rain. We just thought to see the vertical profile, so we focused on +3 hour, such that we get a maximum LWP at least for the CCN 100 case, and also there is enough LWP in both cases. And also we focused on this 7 hour where this total ice water path shows a second peak. So here you can see again from radio sound initialization, left is for model +3 hour lead time, and B column shows model +7 hour lead time. And here left column you can see the A for rainwater mixing ratio, it's in milligram per kilogram, and this is cloud liquid water in B. And bottom it's a total cloud fraction, and D it's a liquid cloud fraction. And same in the right panel for the +7 hour lead time. So as we see, we can see like increased rainwater mixing ratio for this CCN 100 case in the +3 hour when the cloud when you can see it maximize. And in all the three cases, we can see this bimodal structure, but however, we can see that the high CCN cases have more liquid cloud fraction as well as the liquid cloud mixing ratio. And in this +7 hour, we can see that if you notice, this cloud fraction is diminished in the case of CCN 100, whereas we can see a strong peak in the case of 100 and 3000. When we look on this peaking height, we could not see much difference in the three cases if we saw the peaking height. But in the, for example, in the case of CCN 100 in the initial +3 hour time. But if we saw in the 7 hour, we could not see any cloud in the higher case for the CCN 100. So we assume that in the case of CCN 100, so we feel that maybe warm rain or warm process dominates, and as CCN increases, more fine clouds, and it causes deep mixing clouds, and which causes more liquid water and ice phase. So to understand this, we just looked this cross section of vertical cross section and with time. So time evolution of the vertical cross section, and left panel you can see the cloud liquid water mass mixing ratio, and right panel you can see the ice water mass mixing ratio. So as I mentioned, here in the top is for this CCN 100 case, the middle is for the CCN 1000, and bottom is for CCN 3000 case. So we can see clearly the core liquid water in the higher heights for this high CCN case, which leads to high ice clouds compared to the CCN 100 case where though ice clouds are there, but its amount is very minimal. That we can see in the next slide. So here is again same thing. Left panel is a liquid cloud fraction, and the right panel is ice cloud fraction. Top panel shows this for 100 case, and middle panel for 1000, and bottom panel for 3000. So right panel again, top for 100, middle for 1000, and bottom for 3000. It's a ice cloud fraction. So you can see that the ice cloud fraction is very minimal, or just over the percentage wise is around 0.05 percentage. Whereas in the case of CCN high, we can see that ice cloud fraction is more, and you can see a anvil kind of structure. And here you can see that the above over this region we can see a slight updraft. I don't know, is it due to convective inauguration, or it's just a small CCN particles are small ice particles are there, persistent there, which cause we have to see this what causes this here it goes further deeper heights. So this aspect has to be looked, but otherwise I feel that in the first cases we have with radiosonde we here warm the clouds did not grow much deeper, so it's like below freezing level mostly, and so warm rain process is dominating. But in the high CCN case we get more deeper clouds which have more liquid water path as well as the ice water path. But we have to, this is just one setup, but we have to see further more cases to understand what's really happening. So again, next we just looked at same cases, but with the D2 initialization. As I mentioned, this is here initial profiles are obtained from a bigger WRF domain, and since initially we did not get much the convection, we have given a perturbation of theta perturbation of 1 Kelvin up to 9 kilometer for this setup. So coming to the D2 initialization, here also we could see the onset of rainfall have same trend, like low CCN have early onset and a higher CCN have the delayed onset. But compared to radiosonde, we can see that radiosonde started around 1 hour the rain onset, but here we can see that the onset is slightly delayed, and the maximum intensity we can't say that like there earlier we has a clear cut decreasing tendency. Here it is delayed, but yeah, maybe it's slight decreasing tendency for this compared to this. But a liquid water path, we can see a clear increase in a liquid water path, and here compared to the earlier case, this high CCN, we earlier radiosonde case, this small CCN, that is CCN 100 case, we get a bit of gropal as well as ice water path, and we can see a total ice water path grows up to 20 gram per meter square. And coming into this D2 again, we just looked at these vertical profiles, which also shows like more or less 3 hour we get maximum rainfall from the QR, and which got decreased. And here we could not see much double or increased cloud fraction at higher heights, but we can see in the plus 7 hour we can see that increased cloud fraction at higher heights. So here also the evolution, and you can see that compared to the earlier case with the low CCN, here we can get still I think I missed one slide here. Ice phase is there, which I think I did not add. I'm sorry. So what I found is that compared to the radiosonde case, CCN 100 has slightly more ice clouds, so it goes slightly deeper compared to the radiosonde case. So it's like a more in a mixed phase regime. And this is for the D1 domain. D1 domain also we get like same onset, like early onset for low CCN case, and delayed onset for the high CCN case, and the amount also we get smaller for maximum amount smaller for the high CCN case, and liquid water path also shows a same trend. But you can see that in this D1 set we have very minimal like a ice phase for this D1 and D1 with 100 and as well as with 1000. Only 3000 has significant ice phase, which is clear from here. We can see that even though the magnitude are there, but still it's a slight. And if you see the cloud fraction, this is coming from a very small area, less than 0.05 percentage area, which we can see clearly ice phase only from this ice cloud fraction only from this uh, from the CCN 3000 case. So this currently we have in a preliminary stage, we have to further look what causes this difference. First, our thing is that decreased warm rain production as we go for high CCN, and the precipitation comes mostly from the ice phase precipitation. This is really visible in the case of radio sonde, and but we have to see more test to confirm or to further analysis to confirm the things. And further we would like to right now in this case we have kept aerosol as fixed, or I can say CCN as fixed now. So further using casting, we would like to see the aerosol process, role of interactive aerosol process on mixed phase clouds and its feedback on turbulence. Yeah, that's it. Thanks.
Yeah, thank you, Anuroj, for delivering this talk. Now we are open for a few quick questions.
Can I ask a question? Thanks for your nice presentation, Anuroj.
Okay.
Can I speak?
Yes.
Yes.
Yeah, okay. Thank you. So a quick question at your 11th or 12th slide. So you are showing a D2 area, means more larger area for things. There after 6, there is a secondary, means maximum peak after 6 hours. What is the reason for it in your presentation?
Yeah, I can. The radio sonde or radio sonde not. Yeah. You
You're
can
muted.
see that, yeah, this 7 hour, you can see that it's like a peaking more in the case of CCN 3000. So, yeah.
Just asking what could be the reason for it.
Yeah, I don't know exactly, but we have to see that is there any kind of aggregation happens over that region such that it enhances more things. But we have to investigate on that level what could be the which might be due to some kind of aggregation. Might be, I don't know.
Okay, thank you.
May I ask one question?
Yeah.
Yeah. See, Anuroj, we have also provided observations of CCN spectra and other details.
Okay.
Have you used any of those?
Ma'am, we did not use right now. We are only in the preliminary stage actually. We would like to use further.
Yeah, it would be worth comparing with some of the observations we have given.
Yeah.
So that yeah.
Yeah, I just thought that because Monk is a new model, so we have to verify the plots. But I did not do that verification yet. Maybe I will do so.
Okay, thank you. Thank you for the nice presentation.
Okay, so is there any other question? Yeah, now actually we have time for general question and answer for next 10 minutes. So any general question can be asked during this session. So, any question regarding today's talk?
Okay, Axel, you are spotlighted. Unmute yourself.
Okay, hi. Thanks for the really nice presentations today. Did I understand correctly that many of those simulations, like the one that Anna-Rose just showed, but also many of the previous studies, didn't have any large-scale forcing, but really have more or less like boundary layer convection developing into deeper modes? So it's really growing only from the small scale, which then I think emphasizes really the differences between the microphysics. Whereas if you would have some large scale forcing that could, overcome or, weaken some of these sensitivities. So do you discuss this for these monsoon cases somewhere?
Thara madam, can you reply to this question?
Yeah, Axel, this is a great question. Actually, I had a similar thought.
It's a very nice question, and I want to thank you for asking that. Basically, the original case study that is done with the three domains, three nested domains in the WRF model with the bin microphysics. So that was having the full large scale conditions in it. But then for the case studies, we have taken out the vertical profiles for initialization from the I think 2 or 3 domains, and then the basic run with the 3 domains. And if I remember correctly, the Anuros must have used some of those boundary conditions. I don't know. I think she mentioned about doubly periodic, or can you correct me, Anuros?
Yeah, Excel. I used surface boundary condition, time varying surface boundary condition. It's a fluxus, but from the WRF average for the radiosonde cases, and periodic boundary conditions I used lateral, and forcing I just calculated based on I think Gayatri gave me from the WRF some forcings, and I just checked theta forcing, but not wind shear or not. I did not check much. I just maybe later I will look into that. But I did not, honestly speaking, I did not check much on this wind shear or such forcings. But I provided a theta forcing.
Yeah, just to make sure, I'm not saying that anything is wrong with these simulations. I'm just saying that this is kind of one extreme regime of weak forcing or boundary layer driven convection, and this may have very different microphysical sensitivities that then compared to a more large scale forcing or synoptic scale driven systems. I'm just trying to make sure that you're aware of these differences between these regimes.
Yeah, it definitely. Actually, though we have not pursued it, some of the simulations indeed showed that the boundary layer is boundary layer forcing is quite important in this case, in this particular case.
Of course, it would be really interesting to understand better what is really important for the weather in India. Do you have a lot of these surface-driven systems, or especially during monsoon, are there more large-scale driven systems to understand when you would expect what kind of sensitivity. I think that would be really interesting to figure out.
Yeah, definitely. This will be pursued further. Thank you for bringing up this point.
Okay, great. Thank you.
Yeah, thank you.
Yeah, I think I just want to second Axel's comment for this specific monsoon-related case. I do believe some of the larger scale environment and including the affection of the conditions would change your entire simulation behavior and sensitivities. So it will be really nice to develop a further future case that including these sensitivities related to these large scale forcings, and that would make the case more complete.
Yes, yes, Lulin. Yeah, we will bring up that point. Yeah, there are already more observations now, even with more radar observations, also spatial and in situ observations as well. So that will help us to build a more appropriate case to case for considering the large scale aspects as well.
Great. Yeah, any other questions? Can be more general. If you have any other thoughts, comments, welcome. And probably in 2 or 3 minutes, we'll open up the poster viewing for everybody. Is that the case, Sudasan?
Yeah, I think Dr. Thara will give a brief discussion on like future plan. So
Okay.
that can be 5 to 10 minute session. So after that, we can move to poster viewing session.
Oh yes. Before poster, we have one summary from Tara.
Actually, I don't have much to summarize. All of these guys have done. They have tried their best to do something. But let me try to share something from my screen. I don't know whether it will work. Let me see. Yeah, share the screen. Are you able to see my screen?
Yes.
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 Yeah. What this is one observation that from I think it is from my work. It is an observation done in the peninsular India of the cloud liquid water content and from the in situ observations. Different conditions just during the onset of monsoon over there, and then when monsoon just progressed, just within few days, 21st June to 16 June to 21st June, during that onset period. So what I want to bring to your attention is that most of the clouds that we observe over the region has got a significant amount of liquid water content. Sometimes it is coming close to 3 or 4 grams per meter cube. So this is actually we have a very active mixed phase region in many of those clouds. So basically the warm base, it has a deep warm layer and a lot of supercool liquid in the cloud. So when you fly, I am just showing you one picture here. When you fly in the cloud, actually your aircraft will get a lot of icing on the unheated parts, basically. So this is that's one example. This is another example of liquid water content observed in the northern India with the CAIPEEX observations again, and you can see the temperature range in the color. And I want to show you some other observations elsewhere, comparing with the monsoon observations we have done at -10 degrees C. And you see the hailstorm one, it is which is very high amount, but this is comparable to some very deep convection that is seen over some other parts of the world. And it's not so less that this I just want to point out. And also the number concentration also you can see from some from other in situ measurements. So I just my point here is that whatever clouds that we have observed, there is a very well defined mixed phase region in the cloud, and that is actually poorly represented maybe there are better ways now, say, especially some of the talks that I heard 2 days ago. I see that there are better opportunities now to improve the mixed phase, but I think maybe that we should try some of such methods or observations methods or models in this environment as well, so that we will learn a little bit more about this, and maybe some better clouds can be better represented in the models as well. So I was just thinking that maybe we should, as Jason pointed out, he mentioned about there are other bulk models also. Maybe he mentioned about the P3, or we need to understand that, and maybe we need to know how to modify some of the processes based on the observations even. So I think the last phase of CAIPEEX provided us a very big opportunity to make several of the observations in mixed phase clouds, and we hope that we can bring up new avenues for research in this field, and to enhance knowledge in this field by more interactions with many of there are many we can see that in this group itself there are many people like Shima and all working on mixed phase region, quite advanced models they have made. And we would appreciate if some of you could come together and maybe test case studies from this region. We are ready to help you with any of the observations that are needed as well. I just want to point out that. Thank you.
Thank you, Tara. That's great that we know a lot of more observations available. Very helpful. Any other comments and questions from the audience? Yeah, I think we don't have any. Sudarshan, anything else you wanna announce?
Yeah, no, I think now if there is no more question, then we can move to poster session, and people can interact there, and they can ask if they have question. They can ask to the person presenting the poster.
Okay. Yeah. Before we move to the poster, I have one thing to announce.
Yes.
Which is for everybody that attend our workshop, you're very welcome to leave your kind of a comments in the guest book. That's in the ICCP entrance area. There you can go out of our cloud modeling workshop space, but going further south or towards the downwards, and you can get to the ICCP entrance area. There will be a guest book that for you to leave any comments, message, and we would like to hear from you, your experiences using this platform, and then provide your suggestions for future improvement. So anyone is welcome to do that, and hopefully we can collect more comments from you. So that's my last kind of comments. And then tomorrow we will have another one more day of discussion. Some of the weather modification, cloud seeding related research. Also, all our case leaders will have a breakout room discussion for summarizing our workshop, and then we'll prepare the material to present at the ICCP conference. So that's all I would like to say, and thank you very much for attending our workshop today. Enjoy your poster viewing.
Thank you, Lurin. Thank you.
Thank you, everybody. Thank you, Dustin, for your great leadership. And thank you, Tara.
Thank you so much. Thank you, Vertek and Jason and Alex, everyone who commented and participated. Thank you.
All right.
And to the speakers.
You're right.
You might note that today's, except Wojtek, all speakers are young, especially in this particular case study, all young participants were there.